Okay, guys, we are going to start Chapter 7 today, dealing with Chapter 5, the skeletal system. Now, our first lesson is going to overview the skeletal system as a whole and also talk about its physiology in terms of growth and development. Now, we have several distinct parts of the skeletal system as a whole. We have bones, which we generally refer to as the skeleton, the joints, which allow for movements between two different bones, cartilages, and ligaments. We'll talk about the differences between those as well. And then within the skeletal system, we have two subdivisions, the axial and the appendicular skeleton. Now, the general functions of bones are obviously to support the body. They hold our body up. They protect the soft organs within the thoracic cavity and within the skull. They allow for movement due to attached skeletal muscles. They do store minerals and fats. We'll talk about that in a minute. And also blood cell formation, a process called hematopoiesis. So the adult skeleton has 206 bones. We have two basic types, compact and spongy bone. Compact is homogeneous, and spongy bone has small needle-like pieces of bone, many open spaces. We'll talk about the important role in that later in this lesson. So let's talk about the classification of bones. So if you were to look in your text, in figure 5.1, it goes through all of these. So let's talk about long bones first. Now typically, hence their name, they are longer than they are wide. They have a shaft with heads at both ends, and they contain mostly compact bone. Examples would be the femur and the humerus. This compact bone makes them very, very, very strong as well. Okay, so we see right here the humerus of the arm being a long bone, being the proximal bone of the arm. So we have short bones. Now these are generally going to be cube-shaped. They contain mostly spongy bone. These are going to be the carpals and tarsals. These are the bones that make up the wrist joint and the ankle joint in your hands and feet respectively. So we can see they have this general cuboid shape. They are roughly the same length as they are as width. Now, flat bones, these are thin, flat, and usually curved. They have two thin layers of compact bone that surround a layer of spongy bone. We find these in the skull, ribs, and sternum, respectively. Okay, so we see the sternum right here, and you'll notice this is actually three different bones. We'll talk about why that is important later in this chapter. Okay, we have irregular bones. These are bones that do not fit into other bone classifications, things like the vertebrae that form the spine, and also the hip bones are properly referred to as the coxal bones. Okay, so we see it doesn't really match anything. It's it has this kind of cuboid shape right here, but then has this projection, the spinous projection back here that allows for articulation and also protection of the spinal cord and attachment of the ribs. Now, let's talk about long bones in particular. We have two distinct parts that we've already talked about, the shaft and then the heads on either end. The shaft is referred to as the diaphysis, and it's composed of compact bone. The epiphysis or epiphyses are the ends of the bone, composed mostly of spongy bone. Now, what I do want to point out is what we see right here, the proximal and distal epiphysis. Now, the epiphyses are different. They have different anatomy based upon whether they are proximal or distal. Now, this is because they have different physiologies. They can move in different ways. A good example of this right here appears to be the humerus, and the type of joint that we have is probably you've probably heard the name, a ball and socket joint. That's why we see this rounded end right here, allowing for a full range of rotation at the shoulder. And then down here, we have the distal epiphysis, and this is going to be a hinge joint, or what we call the elbow. Okay, so it simply goes back and forth in one direction. Now, within this, we have the medullary cavity, we have compact bone, and then this covering that we have called the periosteum on the outside. And then within the epiphyses, we find spongy bone covered with the periosteum and articular cartilage, which will help to decrease friction. We should know that from chapter 3. So, the periosteum is this outside covering of the diaphysis, and it's fibrous connective tissue, and the Sharpie's fibers will secure the periosteum to underlying bone. It's very, very, very tough, and we need it to be to protect the bone. And then we have arteries, which will pass through both of these and move into the bone cells into the bone to provide the bone cells with nutrients. So we see right here we have this artery surrounding, passing through the periosteum, and then passing through the Sharpie's fibers into the what are called the central canals right here, providing the bone cells with nutrient, and then we find yellow marrow within. Now, this articular cartilage, it covers the external surfaces of the epiphyses. It's made of hyaline cartilage, and it decreases friction at joint surfaces so they do not rub together. Okay, now, the dividing line between these two we call the epiphyseal plate. So it's a flat plane of hyaline cartilage seen in young growing bone. And when you transition from adolescence into adulthood, anatomically and physiologically, we end up with the epiphyseal line. And it's a remnant of the epiphyseal plate that can be seen in adult bones. Now, there's a pretty high likelihood that if any of you have broken your wrist or your ankle as a teenager, that it was broken at the epiphyseal plate. My older brother, when he was 13, he was playing basketball and fell backwards, and he broke both bones of his lower right arm at the epiphyseal plate, and it looked like he actually had two wrists, and that it was broken right there at the epiphyseal plate. Okay, so this little line right here, that's where he broke both of his. Now, obviously, this is the shoulder. It would be down towards the hand instead of the shoulder. Okay, now the medullary cavity, this is the cavity inside the diaphysis. It contains yellow marrow, which is mostly fat in adults, and red marrow for blood cell formation in infants. So we'll see that transition from red marrow to yellow marrow by adulthood for fat storage. Now, our bone markings. So we do have specific bone markings on our cells, on our bones, and these serve as attachments for things like muscles, tendons, and ligaments. It's also passage for nerves and blood vessels as well to be able to provide those blood cells with nutrients and also some form of communication. So in terms of our bone markings, these projections that we have, projections or processes, these grow out from the bone surface, and depressions or cavities are indentations or places that move in. Table 5.1 outlines all of these, and you can use this as a reference when completing your assignments. It goes through all of the different types that you would see on the bones, and you'll often see these used for directional anatomy as well. You can see that we have the medial and ones like the medial epicondyle. You'll see this directional anatomy used throughout all of these. Okay, so let's talk about the microscopic anatomy of bone. So we have what's called an osteon or a Haversian system. Now, this is a unit of bone containing a central canal and these matrix rings. So the central Haversian canal is within the middle. It carries blood vessels and nerves that will supply those nutrients. And then we have these perforating canals, or Volkmann's canals, that will allow it to radiate from the central canal. They are perpendicular to it, and they carry blood vessels and nerves as well. So the best way to see this, obviously, is with this diagram that we see, figure 5.3a. We see this central canal right here as it passes through, and then we have these perforating or Volkmann's canals going in between. Now we see these terms right here. We're talking about this osteon or Haversian system and the lamellae. We'll talk about lamellae and another term called lacunae in just a second. So lacunae are going to be cavities containing bone cells or osteocytes that are arranged in concentric rings. The lamellae rings are around the central canal, and they are the sites of lacunae. So lacunae are within lamellae. Okay, so we can see this individual lamella right here, and then we see a ring of osteocytes, lamella, osteocytes, lamella, osteocytes, lamella. Okay, so the lacuna is where we find these right here, and then they are surrounded by each. So these osteocytes will continuously grow and break down bone. We'll talk about that in just a minute. So these canaliculi. Okay, I'll say that again, canaliculi. These are tiny canals that radiate from the central canal to lacunae, and they form a transport system connecting all bone cells to a nutrient supply. Now, do not mix up canaliculi with these Volkmann canals. So we go back right here. These perforating canals, they are not the same as the canaliculi. Okay, so we can see right here the canaliculus or canaliculi, they will connect one osteocyte to another to ensure that they all receive the same amount of nutrients. Okay, now Formation of the human skeleton. Now, in embryos, the skeleton is primarily hyaline cartilage, and during development, much of it is converted into bone. However, cartilage does remain in isolated areas, the bridge of the nose, parts of the ribs, the joints, and even the ears. Now, there's a lot of debate as to why this is, but one of the most simplistic explanations for it is that it is those are areas that are exposed or could routinely come in contact with external forces. Now, because of this, it's good for them to be flexible instead of a simple hold fast, so to say, mentality. So you think about your ears. If you are walking through the woods and you catch your ear on a tree branch, because it's cartilage, it can easily bend instead of breaking like it would if it were bone. The same for your nose. If any of you play sports, if you've ever been hit in the nose by a ball or another player, in a basketball game, you could easily see the benefit of that. Your nose will bend. You may have a little bit of a nosebleed, but it's not going to break. Now, you can actually break that cartilage off from the bone. We'll see that when we get to the axial skeleton. We'll see where the bony part stops. You can break that. It is painful. It has to be reset properly so that it heals straight. Now, bone growth, this process that we call ossification. Now, these epiphyseal plates allow for lengthwise growth of long bones during childhood. So new cartilage is continuously formed. That older cartilage becomes ossified or converts into bone. So the cartilage is broken down. The enclosed cartilage is digested away, opening up a medullary cavity, and bone will replace that cartilage through the action of osteoblasts. Now, bones are remodeled and lengthened until growth stops. So bones are remodeled in response to two factors. So our blood calcium levels, the amount of calcium that's in our blood, and the pull of gravity and muscles on the skeleton. So bones grow in width, called appositional growth as well. Now, I want to talk about this these two bullets right here. So blood calcium levels. If you think, you may hear your grandparents, great-grandparents, maybe even your parents talking about they need to take a calcium supplement. Well, that's to help maintain bone health. If you were to not maintain bone health, we see a general shrinkage of the average adult, and we do actually see this. Now, this other one, the pull of gravity and muscles on the skeleton. So if you are an athlete and you are in the gym frequently, exercising, working out, doing all of that, your bone mass will actually increase because those muscles are pulling on the skeleton at those projections that we talked about back in table 5.1. Okay, so we see right here, we see this transition, figure 5.4a, of the bone in an embryo, and then in a fetus, and then in a small child. We see here that we still have a cartilaginous epiphyseal plate, okay, right here, and that this portion right here will continuously be converted into bone until growth stops. We see this articular cartilage covering the end to decrease friction as well. Okay, so figure 5.4b outlines these two side by side. So our cartilage grows here, it's replaced by bone here and here, and eventually will, as it continues to grow, bone will be reabsorbed here. Okay, we see this outline of where the bone was, and it will continue to grow following appositional growth here, and then bone will be reabsorbed from what was right here. Okay. Now, our types of bone cells, as we look at them as a whole, we have osteocytes. These are our mature bone cells. We have our osteoblast and osteoclast. Now, these are opposing types of cells. Osteoblast are bone-forming cells. Osteoclast are bone-destroying cells. So the question is, why do we need both? Well, we exert a lot of force on our skeletal system, and we need to continuously repair it and maintain it. And the breakdown of bone matrix remodeling and the release of calcium is done by that osteoclast. So if your blood calcium level gets very low, your osteoclast will begin to break bone cells down to release that calcium. Then your osteoblast would remove it from the blood and get it back to the appropriate level. Okay, so we need these two to stay in balance, very much like that homeostatic mechanism that we covered way back in chapter 1. Now, if you have any questions, please post them in the comments below, or you can send an email to mr.tucker.schs@gmail.com.